So if you recall from your old studies in geometry, we would describe a line as tangent to a circle if it struck the circle exactly once. And it's considered secant if it strikes it twice, and obviously if it doesn't strike it at all, we don't talk about it. But it might be natural to discuss, instead of just for a circle, what happens for some arbitrary curve, like here. Can we discuss the idea of what it means for a line to be tangent to a curve? And in fact, how can we relate this back in a way that makes sense for the original circle? And so what we're going to find is an algebraic way rather than a geometric way to describe this. So if I have this diagram, and this black curve is the function value. And what I'm looking for is this green line. This line where I'm striking it exactly once. Exactly once. So how do I do that? Well, I may not know today, but what I do know is some topics from algebra, specifically the idea of a slope. So I know that the slope is this delta y over delta x. Remember, it's the change in y over the change in x. The problem is I'm trying to find the slope at a point, and usually for a slope we need 2 points. Well, not usually. We always need 2 points, right? We have to find the change in y and the change in x. So what I'm going to do is, instead of thinking about, I'm going to fix this point x value c, and the y value is f of c, but I'm going to have this sliding scale. I'm going to parameterize, or think about some distance away from c. So I'm going to add some number to it, and I'm going to call it delta x. So that's going to be just the change in the width at x here. And so whatever I have for c, I have this c plus delta x. So I can evaluate the function at c plus delta x. Now, there are some nuances here. You need to make sure that the function's always defined there. We need to have a continuous function to even talk about this. So there are some nuances, but let's set those aside for just a moment and think about this as, okay, I have some change in x and some change in y. Okay, well, then I can say, all right, I need the second y value, which is the function value here, minus the first y value. And then I have the second x value here, minus the first x value. And of course, the c's cancel here, so on bottom what I have is this delta x. And on top I have f of c plus delta x minus f of c. Now, generally speaking, what we know is we're going to know this function value, and we're going to know this x value. But since that delta x is moving, we might be able to evaluate it, but your answer is going to have that delta x in it. So what we're trying to do is go from this orange line, hopefully you can see that, it looks like a light peach to me. From this orange line, we want to pinch this delta x really small, and you'll see that orange line kind of slide, and eventually, as these values get closer and closer, and I'm going to draw a few just for funsies here, right? If I drew one through these 2 points, and those 2 points, and those 2 points, and I keep drawing them thinner and thinner, or more and more thinly, I'd eventually arrive at this green line. And what we find is, since we're taking that delta x, and we're making it smaller and smaller, this is it's natural to discuss it in terms of the limit. We want to describe that limit as that delta x quantity goes to 0. So ultimately, this piece here, to find that slope of the tangent line at x equals c, we might call that f prime. So that little apostrophe there is the prime notation. F prime at c. This notation, df dx, with a line at x equals c. You'll see this sometimes. Or even just the derivative of f at c. All that stuff, what we want to do is we want to find this limit. And we're going to do some examples to compute the limit, but fundamentally the idea here is we're going to pinch that down so that we don't need 2 points to define this. We only need 1. And in fact, if we go back to our definitions of a line and get the function for a line, you can usually pick out the slope there, but we'll be able to apply this methodology and show that we can get the value at any given point.